Hello and welcome to the webinar on targeting MATLAB algorithms to FPGAs. My name is Robert Anderson. I'm a principal application engineer from MathWorks. I specialize in signal processing and in targeting hardware design flows. People are interested in model-based design. By the end of this webinar, I want you to understand how you can design and verify FPGA implementations using MATLAB. Describing an implementation in an abstract language such as MATLAB and targeting hardware implementations is very powerful because it can result in significant savings in both the development as well as in the verification interval. By using the methods I'm going to talk about, our customers have reported significant savings. We will make this case by focusing on a few important areas. The first of which is how you can use model-based design to target Altera FPGAs, floating to fixed point conversion, and how to use these coding styles to create efficient hardware implementations. On the verification side, we will look at floating point verification, fixed point verification, co-simulation between MATLAB and HDL using ModelSim, or actually you could also use Cadence Incisive, and then FPGA-in-the-loop or FIL hardware co-simulation. This presentation will take about a half hour. So how can we verify that our hardware implementation matches an abstract system specification? And what can we do to iterate on the designs faster? I mean, this is the million-dollar question. You know, what kinds of things can we do to actually speed up this process? Traditionally, there's a disconnect between the algorithm level descriptions and what's going on in the hardware. What we're going to talk about today is a mechanism that will show how to bridge the gap between the algorithmic descriptions and the hardware implementations. So the solution for this perennial question is using model-based design. It gives you the ability essentially to tie a golden source written in MATLAB at the top level with the hardware implementation targeting an FPGA. You have the ability to design, simulate, and validate your algorithms in MATLAB, also in Simulink, although today we're focused more specifically on MATLAB. We'll talk about the capabilities of automatically generating HDL code, and then how do we go through a verification process for this. So think back to your college days when you were taking classes in the engineering department, specifically digital signal processing classes. Do you remember learning about the LMS filters? These are a class of adaptive filters that are used for optimal filtering applications such as echo cancellation. The idea behind the filter is to adjust the coefficients. So here's our standard convolution. Where we'll be computing an output. In this case, it's going to be an estimate. We'll take the input and then convolve it against some coefficients, which is what we have here. Then the relationship between what these coefficients are is actually related to the error signal, which is the difference from our desired signal and what actually gets computed by the filter itself. So the idea is to actually compute the coefficients to minimize this error signal. Here's what this particular echo canceller looks like in action. If you think about a phone call where someone is on this end, this is known as the far end, and you are here on the near end. Typically, there's going to be some sort of coupling that occurs between the speaker on the phone and the microphone on the phone. So this would be where the speaker is playing out what is heard, and this is the microphone where you'd be speaking into it to speak to the person on the far end. So the coupling here that might occur for old landline systems included things like the hybrid. If you're on a speakerphone, it can include the room that you're in when you're on the speakerphone. There's a coupling that occurs in there. On a cell phone, it can occur through the physical packaging of the phone itself and through some coupling between the speaker and the microphone on your cell phone. This signal here is what the LMS filter, which is this model here, the echo canceller model, or is attempting to estimate. So this y hat here is an attempt to estimate the actual coupling that is occurring in whatever this media is. As the filter converges, the idea is that the error here is supposed to get smaller and come down to some optimal small level. So that's basically what the LMS filter is designed for. Here's a view of the Stratix 5 hardware. We're running FPGA-in-the-loop verification for our LMS filter. On the left side of the board, you can see, it might be a little bit difficult to see, but there's a programming cable. And then on the top of the board is the cable used for communicating between the host PC and the Stratix 5 board. We're using a daughter card here for Ethernet communication between the host PC and the board. In the back, we are running FPGA-in-the-loop verification where the device is going through programming. Once the bit stream has been downloaded onto the FPGA and the Stratix 5 daughter card, the FPGA-in-the-loop or FIL verification begins, and we can see the simulation results thrown up on the screen. On the top left, you can actually see the echo canceller as it's converging. That's the difference between the estimate and the acoustic coupling that was coming in on the input. So it gets better as time progresses. Here's an overview of what the design flow looks like, starting with an abstract algorithm, moving all the way down through hardware implementation. You can start in floating point MATLAB, describe your algorithm, and then from floating point MATLAB, we go through a process, floating point to fixed point conversion, using a MathWorks tool called Fixed Point Designer. This floating to fixed point conversion phase is typically iterative in that, depending on the complexity of your algorithm, you may go through it several times in order to settle on what the optimal result is. Floating to fixed point conversion is typically a art in that you're attempting to balance word length against quantization noise, against the critical path of your design, and ultimately the sample rate and the footprint that the final implementation will target. So all of these factors, which are seemingly in contention with each other, need to be taken into consideration when converging on what the optimal result is. Once the fixed point design has been verified to your satisfaction, the next step in the flow then is to go through HDL code generation. So this is the point where maybe we will target some hardware-specific optimizations like memory mapping, registering, pipe stage insertion, loop unrolling, and hardware-specific kinds of optimizations. Once we've generated HDL code, the next step then is to go through a verification phase where we've taken the stimulus and reference results generated during the floating to fixed point conversion process, and we actually use those as a part of the verification during the HDL co-simulation. So there's a couple different kinds of verification that can be done. One is HDL co-simulation, where we run a black box version of the generated HDL code against the MATLAB source. There's FPGA-in-the-loop, where we will take the MATLAB test bench and run this against the actual bit stream or the hardware implementation that is put on our Altera FPGA evaluation board. There's also a standalone co-verification phase where we would take fixed point stimulus and reference results that are generated here during the fixed point verification phase and actually run those standalone as a standalone HDL verification. That we would also do during this phase here. Final step in the flow then is to take this verified HDL and then generate a Quartus 2 bit stream, or maybe encapsulate this into a larger design. Udian Sina, product marketing engineer from Altera, will talk about Qsys IP encapsulation later on during our presentation. So the big question that people ask is, all right, this is all fine and dandy, but how do I get good results on my FPGA? How can I guarantee that the generated MATLAB is actually going to give the kind of results that I'm looking for? Well, there are three general things to keep in mind in order to ensure this. First of which is make the MATLAB code hardware friendly to begin with. So when you start writing the MATLAB, think about what the ultimate hardware implementation should look like. We'll talk about that in more detail. The second thing is leverage the HDL Coder workflow. This means use the optimizations that the tool provides you, things like memory mapping, breaking the critical path, the floating to fixed point conversion, fixed point optimizations that you can do, and the kind of IP that you will integrate during the floating to fixed point conversion phase in order to create an optimal implementation. And then finally, leveraging the back-end tools, the synthesis, Quartus II synthesis, and implementation. Leveraging optimizations in these tools and encapsulation into a larger system-level design. So how do we author MATLAB code for good and efficient hardware implementation? Let's touch on just a couple of quick points as we go through this presentation. The MATLAB source, we'll start with the test bench. Here's where the stimulus gets generated. X is the far end signal, which is essentially the person on the other side of the phone talking to us. NE is the near end signal. This would be us and our voice energy speaking to the other person. Y is the output from whatever the coupling medium is, whether it's acoustic coupling for maybe a speakerphone or for coupling through a cell phone, or it could be a hybrid if we were talking about a wireline telephone system. And then D is the desired signal. Moving down further, at the very bottom of our test bench file, here is where the plots are generated. And then right here, from line 24 through 31, here's the call to the design function. So here's the LMS filter. This is the part that we're targeting for hardware implementation. So this is the separation between the test bench and then the part of the design that we're targeting for hardware. Let's look at the hardware. Here's our LMS filter function. Here's the entry point, the function declaration, inputs to the system. Persistent variables here, our filter coefficients are declared as persistent variables. These are variables that will have a lifetime of longer than one function call. So these are things that you want to be around for the lifetime of your filtering operation, if you will. So things like coefficients, constants, you would have declared as persistent variables. Tap delay lines, so right here in our code, this is the function definition for the tap delay line. This is also declared as persistent. So persistent variables could be implemented as flip-flops or maybe memory structures. You can see the code is very readable. Here's where the coefficient weights get updated. Here's the MATLAB console. Let's create an HDL Coder project. I was on the Application tab. Go down to Code Generation, select HDL Coder. Create a name for our project, LMS filter. Now here, this is asking us to specify the MATLAB function. that we're targeting for implementation, which is this one here. You'll notice the inputs are undefined at this point. Let's add the test bench as well. This will give us a context with which to go through the type declarations, type definition, and then ultimately the floating to fixed point conversion. This is the HDL Workflow Advisor window. This is a very nice cockpit that you can use, especially if you're not familiar with how to use HDL Coder for MATLAB. It will take you through step by step, starting with floating point, going through floating to fixed point conversion, HDL code generation, verification, and then into synthesis and place and route. So the first step then is to actually define our input types. We can do this by running a floating point simulation. This isn't necessary. I could actually go through and define these here as well. So you'll see that they're all double precision scalar values. Once we've done this, the next step in the flow then is to go through floating to fixed point conversion. Here the simulation is running. The floating point results then are instrumented in MATLAB executable files such that the dynamic range can be assessed. The min values and the max values can be assessed dynamically in order to aid in the floating to fixed point conversion process. Here are the inputs to the filter. Here are the outputs from the filter. Here are the coefficients. Here are the simulation minimum values and the simulation maximum values. These are the values for simulation-based proposal. So these proposed types over here on the right are proposed fixed point types that were obtained based on what the simulation types were here. There's also a static analysis, which I'm not going to go through now, where you can actually put in the minimum and the maximum values, and instead of running a simulation, there's a static analysis on the data path and the arithmetic operators that could be used for assessing word length as well. This is powerful because floating to fixed point conversion is something that's historically very tedious, especially when designs become complex. It's excellent to be able to have a way to quickly iterate and quickly modify word lengths on our designs in order to get something that makes sense. We can actually go in and modify these proposed results. You can modify any of the variables within your design. Say I want this to be a 5, or say a 7, 4. So we can actually change any of the variables here. We'll change the error signal. When I modify it, you'll notice now that it's emboldened, so you can see which ones were declared by Fixed Point Designer and which ones you declared on your own. Since I've modified this, I'm going to rerun Fixed Point Conversion. Let's look at the new results. Now if we look at the echo canceller estimates here during the conversion, the convergence phase, there's no appreciable difference. But the nice thing is you can quickly go through and assess any fixed point performance. Once we're happy with the fixed point results of our design, the next step is to go through HDL code generation. You can target VHDL or Verilog. You can also specify checks, coding style checks of HDL against various industry standard, or you may have your own internal standards. We've got a default standard that you have the option of using, or you can specify no coding standard checks at all. I'm going to generate a report along with this so we can actually cross-probe between the generated VHDL and the fixed point, the generated fixed point MATLAB code. For co-simulation, we do need to scalarize the vector output. So if there's any vectors in your design, you have to go through an explicit scalarization. For our design, we'll leave the reset as asynchronous. This could be specified as synchronous as well. You can specify the assertion level. And for VHDL, you can also specify whether or not you're going to use numeric standard or standard logic arithmetic. Some of the optimizations that are available include memory mapping, registering the I/O in order to break the critical path, insertion of pipe stages into the data path, and then also you can pipeline individual variables by specifying those variables from the MATLAB source code here. Constant multiplier optimizations are also available. Canonical sign digit is a commonly used method for doing iterative or basically shift adds instead of using an entire dedicated DSP48 block. Let's look at the report that was generated. From the report, we can look directly at the generated VHDL. Within this code, we can cross-probe back from the generated VHDL into the fixed point source code. So the VHDL code is quite readable. Here's where the coefficient weights get updated. This is the VHDL that was generated for that. And you can see how here we can actually cross-probe back into the original MATLAB source code. So it's very quick and easy. This is the fixed point MATLAB generated from the original floating point MATLAB source code during the floating to fixed point conversion process. Once we've completed the HDL code generation, next step is HDL verification. There are three different kinds of verification available. First of which is a verification using a standalone generated HDL test bench. The next one is verifying with co-simulation, where you verify between MATLAB and the generated HDL code. And then the final one is an FPGA-in-the-loop or fill verification, which we looked at during the first part of this presentation. I'll click here and we'll run the HDL simulation. So this is a standalone simulation where we will, in this case, actually invoke ModelSim and run a ModelSim simulation. Simulation is complete. We can click down here on the report and look at the results. You could also take any of the generated VHDL or Verilog and integrate that into your larger test environment. The next verification type that you have at your disposal is co-simulation. This is a way to simulate between MATLAB and your HDL that was generated. It requires a capability called HDL Verifier, which is available as an option. So we can run Mentor Graphics ModelSim. We can run it in a batch mode or in a GUI mode. I'm going to put it in a GUI mode here. So this will bring up ModelSim and we can run directly from here. The co-simulation between MATLAB and HDL is very powerful in that part of it's running in MATLAB, and then whatever pieces we're targeting for implementation, we can get their observability in ModelSim. So you can see all of the signals here in the design that we have access to. So depending on what sort of debugging you need to do, you've got all of these at your disposal when you run this graphically. You can also run it in the batch mode. The next step, which we went through earlier, is the FPGA-in-the-loop verification. So this is where we run MATLAB against using an actual FPGA board. We used the Stratix 5 board earlier and saw those results. So we will skip this step and move on to synthesis and place and route. To get an accurate picture of the post place and route timing and resource utilization of our LMS filter, we can take the design and run it through synthesis and place and route, and then look at the resource implementation details of that particular block. So this is also a point where we could take the design and then integrate it into a larger Altera project using Altera Qsys. Udian Sina, my colleague from Altera, will now be talking to you about how to take this design and give you guidelines on how to integrate it into a larger project using Altera Qsys environment.
Thanks very much, Bob, and thank you to the MathWorks for the opportunity to present today. My name is Udian Sinha. On behalf of Altera, I'd like to talk to you about the Qsys System Integration Tool. FPGA designers are constantly looking for ways to improve their productivity. And if you're a veteran FPGA designer, you'll remember the old days when designing for an FPGA meant designing at the gate level. As it became inefficient to design at the gate level, FPGA designers turned to RTL, or register transfer level. And as designs grew even larger, designing with 100% custom RTL became inefficient, and that led to the adoption of IP cores. Now today, designers like you are looking to again increase the level of design abstraction to improve their design productivity. Altera now introduces the Qsys System Level Integration Tool, enabling designers to develop large, complex systems using not only IP cores, but also smaller complete systems or subsystems as building blocks. Qsys is a system-level integration tool that's available in Altera's Quartus II software. Qsys is based on the successful SOPC Builder tool and delivers many key new features and benefits to address today's FPGA design challenges. We'll cover how these 5 key benefits and features of Qsys, system hierarchy, high-performance interconnect, design reuse flow, support for industry-standard interfaces, and real-time system debug can help you improve your productivity when you need it. The first design challenge we highlighted earlier was the growing design size challenge. If you take a look at your FPGA design, you can break down your design into 3 general buckets. The green standard cores represent design functions that are commonly available. For example, here the memory controllers, microprocessors, PCI interfaces, and UART would exist. The blue shaded area are glue logic. Glue logic is all the integration logic that connects your design blocks together. These would include your address buses, data buses, with matching logic, and arbitration logic. And finally, there's the orange blocks. This is your custom logic. This is the part of the design where you want to spend most of your time and resources on. It's your unique algorithm, and this is where your company often expects you to spend most of your time. So what standard cores are available? Well, Qsys offers a wide range of plug-and-play IP, also known as Qsys-compliant IP cores. Qsys-compliant cores range from interface protocol IPs like PCI Express to memory IPs like DDR3 to video imaging IPs like the scalar or deinterlacer IP cores. In the embedded IP world, the NEOS 2 software processors, JTAG, UART, SPI, and RS-232 IP are all Qsys compliant. Today, there are over 100 Qsys compliant IP cores with more to come. Using Qsys compliant IP can help you accelerate your development, so now let's look at how Qsys can help with your glue logic. First of all, instead of connecting hundreds of signals and buses between your multiple design blocks, we can use Qsys to integrate the work for us. Qsys provides an intuitive GUI interface that allows you to make connections between different blocks, effectively connecting many signals and buses together with a single mouse click. After you've described the connections between your design blocks, Qsys will automatically generate the interconnect for you and the interconnect HDL. So now let's look at the design reuse challenge. It's typical for designers to spend a lot of time and effort trying to reuse someone else's design. And most of the time, the original designer needs to redesign their interface just to match your specific interface used in your project. And as a result, they end up supporting multiple variations of their own design. Qsys maximizes design reuse by using standard interfaces. For example, using the Avalon interface makes it easier to integrate because the Avalon interface is a standard interface well understood by Qsys, publicly documented and maintained. Standardizing on an interface eliminates the need to change the design for each project, thus making the design easier to be reused. Many IP cores use industry-standard interfaces for easier integration. However, it is unlikely that IP vendors, FPGA vendors, and FPGA designers like you all use the same industry-standard interface. So that's why Qsys uses an interconnect that supports mixing of different interfaces. For example, here you have 3 masters and 3 slaves. There's a mix of standard interfaces, some using Avalon interfaces and some using AXI. The Qsys interconnect, based on a network-on-chip architecture, is able to create and transport wide packets between the masters and slaves. These wide packets are used to encapsulate the AXI or Avalon-based transactions. Now let's take a look at the design reuse flow. First, you'd import your Verilog or VHDL design into Qsys. Once imported, Qsys will automatically package up your design block with the GUI wizard so it appears like any other Qsys-compliant IP. At the same time, Qsys will add your design block into the component library. Finally, the third step is for you and other designers to add your designs into their systems. For example, here both System A and System B are using design blocks found in the component library in Qsys. Now let's look at the verification challenge. You can shorten your verification by shortening the time you spend on simulation. Take a look at the device under test, which is connected to bus functional models and monitors, all wrapped up with a top-level test bench file. Here are some areas where Qsys can help you get your simulation started faster. Because Qsys uses standard interfaces, you are able to reuse your testing environment, like the bus functional models and monitors. Qsys also provides a suite of verification IPs, including master and slave bus functional models, source and sink bus functional models and monitors, so you don't need to develop them. Qsys also automatically generates a test bench for your system and automatically integrates the bus functional models into a system for you. Qsys also supports on-chip debug to help you debug your system in real time. Qsys allows you to access a system by sending read-write transactions through a bridge IP. In this example, the bridge IP, it can be JTAG or TCP IP, enable your system to be accessible by System Console available from within Qsys. You can then write test vectors into your system and read back the data. Remotely reading and writing into your system can be much more efficient than accessing each individual register. So in summary, Qsys is a powerful system integration tool that can be used to improve your productivity when you need it. And with that, I'd like to thank the MathWorks for the opportunity to present, and I'll hand it back over to Bob.
Thank you very much, Udian. Let's review what we just covered. We went through floating to fixed point conversion, starting with floating point MATLAB source code, create a fixed point representation. We showed how to take this fixed point MATLAB design and generate HDL code from it. We talked about three different kinds of verification: a standalone HDL verification using ModelSim, and then through the HDL verifier capability, we also discussed co-simulation between MATLAB and the generated HDL, and we also showed how to do fill or FPGA-in-the-loop verification with the HDL verifier capability as well, targeting the Stratix 5 evaluation board. Then we showed how to run synthesis and place and route from the HDL workflow advisor when targeting a Stratix 5 device. Then Udian spent some time talking about how to take this generated design and integrate it into a larger project using Altera Qsys. One of our customers, FLIR Systems, has had some great experiences with MATLAB to HDL for image processing systems. They mentioned they were able to reduce their overall design time from proof of concept all the way through to prototype by more than 50%. So they were able to make upgrades to their system in hours instead of weeks. And they're quoted as saying, with MATLAB and HDL Coder, we're much more responsive to marketplace needs. We now embrace the change because we can take a new idea into a real-time capable hardware prototype in just a few weeks. There's more joy in engineering, so we've increased job satisfaction as well as customer satisfaction. For more information, visit mathworks.com/Altera. MathWorks has a variety of different webinars that are available for you. These are recorded webinars, implementing MATLAB algorithms in FPGAs and ASICs, FPGA and ASIC verification made easy, using HDL Coder and HDL Verifier for FPGAs and ASIC designs, introduction to FPGA design using MATLAB and Simulink, You can also contact MathWorks and arrange in-depth demonstrations. We can come into your office, come in on site and work with you, show you demos. We provide training as well. For technical questions, email alteraexpert@mathworks.com. Thank you so much for your time today.